Okay, Assalamualaikum and very good. Now it's a good afternoon. Okay, so last class we did discuss on the three-phase uncontrolled rectifier, and we look into the midpoint converter. So the other name for this three-phase half-wave uncontrolled rectifier is a three-phase three-pulse midpoint converter. Three-pulse midpoint converter. And we look into how the circuit works, whereby in order for us to determine which diode is on at any particular time, we apply these particular rules, whereby at any instant the diode which its anode has the highest amount of instantaneous phase voltage will conduct. So if you look at the waveform, uh, the the diode operation will be from, you can divide that, and then you can know that this is the highest voltage. So diode 3 or blue diode will conduct during that point, and then during this period you have diode 1 or red diode to operate, and then we have diode 2, yellow diode will operate, and finally come back to D3. Okay, so when you have that operation D1, D2, D3, and whenever it's on, there will be a short circuit, isn't it? And therefore VDC will copy exactly what is the output, what is the input voltage. So if we connect to the red phase, so output voltage will copy the output voltage, the supply voltage of red. And then if the diode and diode 1, diode 2, diode 3, so you follow the envelope of the supply phase voltage, isn't it? So that will be the output voltage, and from that we derive for the average of the output voltage, whereby you take one of the pulse, just simply modify this pulse to be in this form, right? So you switch, or you change that to 0 second, 0 radian, and then by doing that you actually change the equation or the waveform from sinusoidal waveform to a cos waveform. Okay, so you have V peak phase cos theta, right? And then you do the derivation, and finally found out that the output voltage can be described by this equation. Okay, so next we look into resistive and inductive load. So in this case, when you look carefully, the output voltage, or there is no difference between the resistive and inductive load. However, when you look at the current, you can see that the current become continuous now. Okay, so small ripple, and when you refer to the input red phase current, then it will follow this shape 0, and then it will follow the IDC, the ripple of the IDC, and next we're going to have that at the IR. So that to follow the diode. So this is when diode 1 on, okay, and then you have diode 2 operate here, and then somewhere the diode 2, the diode 3 will operate at that period, and then finally come back to D1. So whenever D1 on, you can see the current at the phase, red phase current, the red phase. So you have that. Okay, so next is we look into the effect of line source inductance on current commutation for three-phase half-wave uncontrolled rectifier. So we know that with a purely resistive load, the current change from, for example, from the beginning here, you have the current flow from blue phase, and instantaneously after this 30-degree, the intersection between V red and V blue, right after that intersection, the current in the diode will commutate to red phase instantaneously. So it happens with a sharp rise and sharp falls, isn't it? So you can see that there is a falling of current from blue phase, and then you can see that the current now flow at the red phase. So that happens instantaneously. But in the case of purely inductive, when we have a line and source inductance, okay, so we consider line source inductance here. So again, this line and source inductance come from the cables and also the winding of the transformer, isn't it? And again, we're going to replace that to ease our analysis. To simplify our analysis, we're going to replace that with a highly inductive load, and therefore you just use the ideal current source. Yeah, so you put in the ideal current source, and we try to look into the transfer of current at this point. So we know that this period you have D1 red diode transfer to diode 2, isn't it? So the transfer of current is from D1 to D2. So if you can look further, this is D red, and you want to transfer to dy. So in order for you to explain, you need to refer to one particular point. So we start with this transfer of current from D1 to D2. Okay, so from dr to dy. Okay, so we know that during that, when it transfer to D2, we can see that the current from the red phase will reduce to 0, and then we have the current from 0, the yellow current will flow from 0 to the circuit current, which is the IDC, to the output current of IDC. And during this window, you can see that this is the overlap happens. So we have an overlapping phenomena here, or this is also known as commutation interval. Okay, from 0 to mu. Right, so from 0 to mu. So the current from IDC 0 IDC to 0 to IDC, and we can see that the current through red phase is from IDC to 0. So we can see that. If you look further, if you can look carefully on the output voltage, so the pink voltage here represent the output voltage. So if you look carefully, this red phase pink voltage or the output voltage here run in the middle between the two waveform here. Look at that. If by observation, this is only for by observation, we can see clearly that the waveform is run in between the two phase voltage here. Red phase, so it is in the middle between the two waveform. It's sort of the average between the two waveform here, isn't it? So now let's look at how to get the output equation, the average of the output equation. So we consider first, remember this is the transfer of current from red phase to yellow phase. Okay, so we start with this equation for VDC, and during the overlap, we take this equivalent circuit. We have V red and V yellow, and then we have red current flowing that direction and yellow current flowing that direction, and you have IDC flowing at the output and come back to here, isn't it? So if you can further complete the circuit, you can see that it's actually come back to that point, isn't it? It's a complete circle. So this is during overlap, and by doing that, then you do the KVL. So you must follow this correctly, and then we have this equation VDCT, which is the output here. This is also VDCT. Don't worry about the notation. The V out and VDC is the same. So it is the VDC equals to VR minus. So we just take this route, this path after that. So we have minus VR plus IR LS dir over dt plus VDC. So you have this equation, And for this path, for the other path, we can see that it's a minus Vy plus Iy, Ls multiplied by diy over dt plus Vdc. So you have two equations here, right? You have two equations, and then you add both equations that give you this equation 2Vdc equals to Vr plus Vr. However, by KCL, at that point, if you apply the KCL, Kirchhoff current law, IR plus IY equals to IDC, isn't it? And when you do the call it differentiation, if you do the differentiation, you can see that dir plus diy over dt actually equals to dir plus dir. This is also a rule, some rule for differentiation. And if you integrate, if you differentiate the right side, the IDC a constant current, of course you get the 0 because it's a constant value, isn't it? Since IDC is constant value, so both equation here become 0. So this equation become 0. So this is 0. Therefore, what left is only VDC, VR. So VDC at the end, VDC equals to that equation. So that means when we look again, this is the average between the two waveform VR of Vy, isn't it? So that proof our observation just now. We say that the ping or the output voltage run in the middle between the two, which is the average between the two, isn't it? It's the average between the two waveform. So by equation just now, by derivation, yes, we proved that. We know that VDC during this time equals to VR plus Vy divided by 2. So that means if you pick this point, VR plus Vy will be somewhere here, and then you divide by 2. So you get that, we call it the voltage here. Right? So it is in the middle of between the two waveform. VR plus Vy divided by 2. Okay, so that gives you the VDC. Now we're going to look into the commutation interval U. What is the angle of commutation here? So in order to do that, we need to draw the commutation current IU. Okay, so we need to draw following the point that we are referred to. So we are referring the transfer of current from Vrad, red phase voltage, to yellow phase voltage, isn't it? So after that overlap period, you can see that the current start to flow exactly on in the yellow phase, isn't it? Yeah, so that's why in here, for the equivalent circuit here, you need to draw the current path, okay, the direction of the current flow in the circuit. So that current must follow the yellow current which flow after the overlap period, right? Commutation interval. So you have that IU, and then you do the KVL again around this loop. So you have minus Vy. If you follow this path, it is a minus Vy plus Ls diu over dt, diu, now it is a diu, and then we have another one here plus Ls diu, so you get same 2 Ls diu over dt equals to 0, right? So you have that. So convert to radian, so you have diu over deta, and then you integrate left hand side, right hand side, and you get this 0 IDC. So how we obtain that? We look into the current, the yellow current. Okay, we refer to yellow current. Okay, so if you refer to the yellow current, if we refer to that yellow current, it is from, look at the graph, waveform. Okay, so if you look at the yellow current, it is from 0 to IDC. So the integration is from 0 to IDC. And on the left hand side we have 0 to U is 0 to IDC. Solve that. So finally you found out that the U, the angle, is defined by this equation. Was cos 1 minus 2 omega ls IDC divided by V peak line to line. Right. Okay. So next is to look into the average output voltage VDC. First, we already know the equation for the V output, right, during the overlap. And then next, we know the equation for U, the commutation interval, commutation angle. And finally, we need to determine the average output voltage VDC. So, if you refer to that, during commutation interval, the voltage drop across the line that in shaded area. Similar strategy as explained in section 4.2, 4.22 is applied here to VDC. So, which means you know the equation without the source inductance, and then you just simply minus the average of that voltage drop here. Is it? Okay, so that is for our approach. Okay, so we need to find the area of the shaded area here, the loss, the area voltage drop here, and then we take the average of that. So how to get that area? Just simply you need to, you can do this, which is Vy, isn't it? We know that is what is a Vy is, and then you minus that VDC, isn't it? So VR minus VDC, we already know the equation for VDC, and you will get the area under the curve here. Okay, so that what's doing here. So we have 0 to mu minus Vy theta minus this. So this is your equation, Vy theta minus VR plus Vy over 2. That gives you the area here, and you integrate 0 to U mu, and then you solve that, and you find out that is a Vy over R, and we solve again. So if you refer to equation 6.1 and 6.9 just now, you can see that the integration of Vyr from 0 to mu equals to this 2 omega ls IDC. And finally you found out that the average, or the area voltage drop is omega ls IDC, and we know each pulse of the output voltage consists of only 2 pi over 3, which is 120 degree. To get the average, you just divide by that 2 pi over 3. So that gives you 3 omega ls IDC over 2 pi. Right? So this is taken from the previous equation without the source inductance, and then you just minus the voltage drop, the average of voltage drop. So that gives the output voltage equation. So we have this problem 1 given for the 3-phase half-wave uncontrolled rectifier, constant load current. They calculate the overlap angle and the output voltage. So you can use the equation and look into the overlap angle, U, what is the U, and also what is the output voltage. Okay, next we're going to continue with 3-phase full-wave uncontrolled rectifier. Right, to be able to get that full-wave rectifier, we're going to add another 3 identical diodes, and it is arranged in such a way so that we have the diode, this is known as the top group, and this will be the bottom group. Okay, and if you look at this top group, the diode is connected to the positive of the anode of each diode there, and for the bottom group, the cathode of the bottom group will be connected to the positive here. Get it? Right. Anode and cathode, so we have cathode connected to that. So we and this is also known as a P group, the top group, and the bottom here we known as a N group. So we have positive group, negative group. Okay, and you can also rearrange the circuit here to be in the form of just like we have the midpoint converter, isn't it? So if you remove the negative group here, this is very similar to the midpoint converter just now, right? So we add another bottom group and it connected to that in such a way. So this is the to operate as a full wave uncontrolled rectifier. Okay, and if you look further, the labeling of the diode must be, okay, I'm telling you, it must be in terms of D1, D3, D5, and for the bottom group it has to be D2, D4, D6. You need to clearly label or correctly label the uh, the sequence of the diode, so that when you look at the current commutation in the waveform later on, you will see that the current will flow from D1 and then it will commute to D2, and then it goes to D3, D5, D4, D6. Okay, so this is to actually to the labeling, and the arrangement of the labeling here is to follow the circuit operation. So if you label differently, for example D1 here, D2 here, and then D3 here, you won't get when you look into the waveform later on, it will not be a nice sequence between the current commutation, the current operation, the current commuted from one. So this is to, so that's why if you refer to the textbook and notes, mostly all of them are will label in such a way. We have this D1, D3, D5, D2, D4, D6. So you have to memorize the labeling of the diode. So we have red, yellow, blue, and then the load is connected in the output here. And this is also known as a first leg, second leg, third legs. Okay, and the anode of the positive terminal of each voltage supply here will be connected to the midpoint of the leg of the diodes. So this is known as the midpoint of the diodes. D1, D4 is connected to the red, D3, D6 connected to the yellow phase, and D5 and D2 will be connected to blue phase. Right, so now how to describe the operation. So we have, before this we have 3 diodes, now we have 6 diodes to determine which diode is on any time. So for the 3 pulse rectifier, we know that any diode which its anode has highest potential will conduct, isn't it? And we have a supply, 3-phase supply voltage, and then you can consider, you can determine which diode is on. So here you need to add another rules, which is, so this is for the top group, we apply the same rules, whereby for the top group, at any instant the diode which its anode has the highest amount of instantaneous phase voltage conduct, and for bottom group, at any instant the diode which is a cathode has the lowest amount of instantaneous phase voltage conduct. So for the bottom group, you look into the cathode, has which cathode has the lowest amount of resistor will conduct. So let's take example. So now this is the red, yellow, and blue phase voltage. Okay, let's consider at 0 second, 0 degree here. We look into this point. Okay, at 0 second, we're going to look at that point. Okay, so let's determine which diode is on. So for the top group, of course, the highest potential is at blue, isn't it? So if you blue waveform, that will be what? Red, yellow, blue. So this D5 will turn on during this time, isn't it? D5 will turn on this time. And for the bottom group, which diode is at the lowest potential. Now, for the bottom group, let's look at which diode has its cathode at lowest potential. So this is the lowest potential, which is connected to yellow phase. So yellow phase is this is red yellow, so that will be the cathode, and it is connected to D6. So at the beginning, 0 seconds, you can see that D5 and D6 operate. Right? D5 and D6 will operate, and the rest is off. So here we can see that during that time, 0 seconds, there is a current through ID5, and also there is a current through ID6. So this is a current through ID6. So that means the current D1, D5. So this is D5. You can write this is D5, and the bottom you have D6 operate here. Okay, D6 operate that. Okay, so next point we have, let's say, just after 30 degree here. So we know this is 30 degrees. So let's say we are at that particular point. Okay, we are at that particular point. So here we have red at its highest potential, isn't it? So D1, and for the bottom group, we still have a yellow phase current at the bottom group that operates, turn on. So we still have D6 operate at that point, isn't it? So we have D1, D6 now, and just after that point, the current now transfer to, instead of yellow, now it transferred to blue phase voltage, isn't it? So blue phase, which is D2. So the current transfer to D2 from D6 to D2. So if we again, so let's say, let's do this. Okay, let's mark the area here, 2, 3 there, and at the bottom, so we're going to mark that, and mark here. So this is the operation of D5. Here we have D1 operate from there to there. Then we have yellow phase rate, which is, if you look at the circuits, that will be D3 operation. Okay, and then we have D5 operate again this time. Right, D1. At the bottom, you have D6 operate here. The next will be D2. Then we have D4 operate that point. By applying that two rules, you can see that this is the region of operation for each diode. So we have D1, D3, D5, 6. So that means because of that labeling, we can see that the current now start from D1, and then it transfer to D2, then transfer to D3, D4, D5. Look at that. So D1, D2, D3, D4, D5, and we come back to D6 here. So this is D6. So because we label in such a way, in such arrangement, then we can see clearly this is a D1, D2, D3, D4, D5, D6. So if you label wrongly labeled, or you don't want to, but you want to have another labeling arrangement, you won't get this kind of nice sequence. Okay, right? So this is when you label the diodes in this arrangement, then you get that in the waveform. You can see it clearly from D1 to D3, D2, and then D3, D4, D5, D6. Okay, so that's why the reason of we label in such arrangement: D1, D3, D5, D2, D4, D6. All right, so next is how to determine the output voltage here. how to get the output voltage waveform. So in order to get that output voltage waveform, we need to rearrange, as I mentioned just now, we need to rearrange the circuit in that arrangement. Okay, so so that is the top group, this is the bottom group, and this is very much similar to the midpoint converter just now, and we add another bottom group here, and uh, we label this is point P and this is node N, capital P, capital N, positive and negative group here, and we have a common neutral point, so you can put it somewhere here. It's very similar to refer that point. So we have plus minus voltage, and then you have plus minus voltage of V and N with respect to N. And just what we did to the half wave full midpoint converter. Okay, so whereby we have for the half wave, you always have this, that, then you common that, is it? And then you have a resistor, and you come back to the neutral, is it? The neutral. Alright, this is point N, so that will be the PN. The same voltage here, PN. So that also happens here. You label this is point P respect to N neutral. So we have another positive VPN. We also have VNN at the bottom group here, and at the output we have VDC at the output here. So that there is actually the loop at the output side here. If you want to VDC. Okay, right. So next is, we know that whenever the D1, D3, D5, P will follow the envelope of the positive voltage. So here you can simply that this is the output voltage, similar to what we did in the full midpoint converter. So that will be your VPN. Copy the envelope of the positive supply voltage, and for the bottom group, follow the negative. So this is your negative VNN respect to N neutral point. So that is the voltage VNN. Right, so this is VPN, small letter, and this is VNN. Okay, so that is the waveform for VPN and VNN. And finally, if you take this KVL, the output we have plus VNN minus VPN equal plus VDC equals to 0, isn't it? And therefore VDC equals to VPN minus VNN. Right. So the output voltage is VPN minus VNN. So you can see clearly here. So it is. So this is VPN. Right. So here we have, this is your VPN minus. So voltage is VDC is equals to VPN minus VNN. So this is VPN minus of that voltage, so you get more. So that is your will be your VDC. That will be your VDC. VPN minus, this is a minus value, negative value, so minus it become plus. So that's why you have this VDC. And if you look carefully, it is actually following. Okay, you can see it clearly here, right? So if you refer to this, that output voltage is actually, or you can refer to this as well. So this is VBY, isn't it? VBT. Okay, this is the output supply voltage for blue phase, and this is supply voltage for V yellow, isn't it? yellow. So here we have VBT minus VBY, VBT minus VYT. So that actually equals to V line to line of VBY. So here, this is actually VBY, line to line voltage. It is line to line voltage. VBY, between B and Y. So your output voltage VDC actually copies the envelope of the line to line voltage. Very different to what we had in the midpoint converter, half wave converter, because the output of the half wave converter is actually the envelope of the supply voltage, phase voltage, but now for the three phase full wave rectifier, the output follow the envelope of the line to line voltage there. Okay, so line to line voltage, so you get that. And if you refer to the my note before, the beginning, we have the tips, steps how to draw that line to line voltage, isn't it? So if you want to draw a line to line voltage, you must have at least 4 triangle. So 1 triangle, is that the negative, and then another one is the inverting version of that, the mirror image of that triangle. Okay, and then you draw another triangle in between. So you have another triangle in between of that. You must follow this, and the inverting version of that, the mirror image of that triangle. Okay, and then you connect the tip of the triangle. Just connect the tip of the triangle. So that is to and in the bottom group, with that. Okay, and then you just pull that, so you can get the line to line voltage. So that become V line to line. And if you draw that 4 triangles, your 0 axis, the y and the x axis will be at the point, right? And this is 0. You must have that 4 to get this 0 y axis at 0 at this point. Okay, so then there is a tips on labeling. So if you have VBY, you can start from VBY if you like, and next will be VBR, right? And then it's changed to B yellow, V remember. Here, look at the notes before to label. There is a sequence, so you have to follow B here, and then transfer Y to R. Then next, I can't remember, but just follow that. Then you get a correct labeling of each of the diodes here, of the waveforms here. So that will be 60 degree. So if you do that for, so you get one is 60 degree. Okay, one of the paths that will be 60 degrees. So therefore, dB, this is 30 degree, and here you have 60 degree from one pulse to another pulse, 60 degree, and again you have 60 degrees. So if you add all together for one cycle, this is one cycle, from there to there is one cycle. So you have what? You have 1, 2, 3, 4, 5, 6 pulses now. Compared to the 3 pulse midpoint converter, the half wave converter, we only have 3 pulse for the half wave rectifier, but for the full wave rectifier, it is 6 pulses. For one cycle, you have 6 pulses of the output voltage. All right. Next is to determine how to determine the average. So we take one pass only. Okay, we just take one pass of that, and then you shift to the center of 0 here, and that's why it's split into minus pi over 6 at positive, and this become minus pi over 6 because this is 60 degrees, isn't it? We know that this is 60 degrees pi over 3. So when you split, it becomes plus pi over 6 minus pi over 6. So, and that now become the equation now because we pick line to line. It's no longer V phase. It's a line to line voltage, and this become cos theta. It's a cos sinusoidal waveform. Right. So we just integrate and divide by 60 degree. That give you the average output voltage. So that what happens here. You can read clear. So just read the note, the monograph to get a clear sequence. And this is your equation, and this is the minus pi 0 plus 6. Then you integrate that to get the output voltage, and pi over 3 is 60 degree. So you do that, solve that, then therefore the output voltage VDC now equals to 3 over pi V peak line to line. So it's very, you have to go one by one, look into the, you have to master in drawing the waveforms and labeling all the waveforms clearly. Then you will be able to see the movement of the diodes. Okay, so you can visualize. You need to visualize, need to understand, right? Once you understand the operation, then you can clearly see, oh, okay, now you start with ID1, and sorry, you start with D5. And then it's transferred to D1, and it's transferred to D3 for the top group, and the bottom group start with D6, isn't it? Start with D6, and then it's transferred to D2, D4. So your mind should be visualize all this movement, all this communication current operations. Okay, so that's it for today's class. Make sure that you start to from now you always start with a plain paper, and then you start to draw the circuit, label correctly. It takes time, but as long when you practice a lot, that will be make it easy for you to understand circuit operation. So you start with one by one. You have to be disciplined, take some time, be calm, right? Draw the circuit, and then sketch the waveform, and then from the waveform you label each of the diode movement, diode labeling of the diodes. Okay, so take one step by one step, and then try to derive everything. And again and again, I did advise you to do the tables, right? So now you have to have a table, put in Microsoft Word if you like, okay, so that you can add. So you can clearly see, if you put it in the table, you can clearly see, okay, this is a three-phase midpoint converter, this is three-phase full wave converter, so you can clearly see. And then the waveforms, okay, the equation involved, that will make your brain to do the mind mapping to retrieve all the information easily. Okay, all right, see you again next week. Bye bye. Assalamualaikum.